Hello everyone, Mr. Lau here. So I will go through question 5, 6 and 7 in this video episode. Okay, because I think I missed out these 3 questions in my previous videos. So for question 5, in a closed system, 0.85 kg of wet steam with an initial pressure of 8 bar and dryness fraction of 0.75 is expanded isothermally to a pressure of 1.5 bar. Okay, determine the change of internal energy during the process. Okay, so clearly this is a isothermal process, okay, based on this keyword. Okay, so for part A, to get the change in internal energy, right, okay, what do we need? We need both U1 and U2. Okay, so what is U1? U1, we know that it has a dryness fraction of 0.75 and an initial pressure of 8 bar. Therefore, this must be a wet steam. So wet steam, we will use wet steam formula. So U1 is equals to 1 minus X UF plus X UG. Okay, so the X value will be 0.75. The UF will be the UF at 8 bar. So referring to the table, UF at 8 bar, okay, will be 720 plus 0.75 again times UG at 8 bar. So UG at 8 bar is 2577. So calculating these values, you will get 2112.75 kilojoule per kg. Okay, so this will be U1. So how about U2? How do I get U2? So if you look at the question, the only thing we know about state 2 is the pressure, which is 1.5 bar as of now. Okay, so as I said before, in order to predetermine a state, you need at least 2 components or 2 properties. So where will the other property come from? Okay, it comes from the fact that T1 must be equal to T2 due to the concept of it being isothermal. Okay, so T1 must be equal to T2. So what is T1 in the first place? So since 1 is in wet steam, so T1 must be at the saturation temperature. So the saturation temperature at 8 bar, okay, from the table will be 170.4 degrees Celsius. Okay, so with this, we can proceed on to determine what the state of 2 is. So at 1.5 bar, okay, we go to 1.5 bar and we look at the T set. So what is the T set value at 1.5 bar? The T set value at 1.5 bar is 111.4 degrees Celsius. So clearly, okay, this is less than T2. Okay, or in other words, T2 is more than the T set. Okay, so T2 is more than the boiling point. Therefore, we can conclude that this must be superheated steam. Okay, so since it is a superheated steam, so we will refer to the superheated table at 1.5 bar and temperature 170.4 degrees Celsius. So clearly, okay, at 1.5 bar, okay, there is no 170.4. Okay, so therefore we got to do interpolation. Okay, so referring to the 1.5 bar row, okay, we will interpolate between 150 degrees Celsius and 200 degrees Celsius. Okay, so when T is 150 degrees Celsius, okay, U is 2580. When T is 170.4 degrees Celsius, your U is the unknown. Okay, so when T is 200 degrees Celsius, your U will be 2656. Okay, so we interpolate between these 2 sets of values. So with that, we will use middle minus top over bottom minus top. Same thing for the right hand side, middle minus top over bottom minus top. So calculating this, U2 will be 2611.008 kilojoule per kg. Alright, so this will be your U2 value. So with your U1 and U2 determined, okay, we can find the change in internal energy, which is mass times U2 minus U1. Okay, plug in the values together with the mass of 0.85 kg. Okay, you will get around 423.6 kilojoule. Okay, can. So for part B, we are asked to find if the work energy transfer is 600 kilojoule. Sorry, we are asked to find the work energy. Okay, if 600 kilojoule of heat is applied to the system. Okay, so we will use the non-flow equation U2 minus U1 equals to Q minus W. Okay, the change in internal energy, okay, today will be 423.5. Q is 600 kilojoule, and since it's Q supplied to the system, means it's Q in. Q in is positive. Okay, so from here, calculate your W, and this will get 176.5 kilojoule. Okay, and since this is a positive W value, okay, this will be work output. Okay, so finally for C, okay, we are asked to draw the PV diagram. Okay, so first of all, you can draw your bell curve first. So initial stage is a wet steam, okay, at 8 bar. So 8 bar, wet steam around here. Okay, final state is 1.5 bar. Okay, and for the final state 1.5 bar, it is at superheated region, so it must be here. Okay, so since this is an isothermal process, okay, it must follow the isotherms. Remember what is isotherm? Isotherms is constant temperature lines. Okay, so on the graph there is this dotted imaginary line that represents constant temperatures. Okay, so from 1 we will proceed to 2 in this manner. Okay, can. So that's all for question 5. Okay, next we have question 6, but we have a closed system. 1 kg of superheated steam, initial pressure of 100 bar and temperature of 375 is expanded reversibly and adiabatically to a final pressure of 38 bar, and the steam is then dry saturated. Determine the change in internal energy of the system. Okay, so again, to get the change in internal energy, we need both U1 and U2. So to get U1, what is U1? Okay, U1, okay, will be the U from the superheated table, okay, at 100 bar, right, and 375 degrees Celsius. Okay, so from the superheated table, we need to find out these values. Okay, take note, these values is not in the table given to you within the textbook. Okay, because for simplicity's sake, okay, or for conciseness, okay, our table is limited to only a certain value. So 100 cannot be found in the superheated table given to you. So you got to go into the internet and find out the value yourself. Okay, which can be easily done. Okay, so in case you are wondering why this value is not in your notes, okay, because it is not given, or we can only give you up to a certain value. If not, we have to print don't know how many millions of pages. Okay, so for this value, okay, from the internet, okay, you can get it to be 2771.7 kilojoule per kg. Okay, so that will be your U1. Okay, so how about U2? U2 is at 38 bar and dry saturated. So clearly U2 will be the value of UG at 38 bar. So this value is available in your saturated water and steam table. So for this value from the table, you will get 2602 kilojoule per kg. So with that, we can calculate our delta U, which is m U2 minus U1. Okay, so plug in the values together with the mass, 1 kg. Okay, you should be able to get your negative 169.7 kilojoule. Okay, B. What is the heat energy transferred? Since it's adiabatic, so it must be 0. Okay, so take note, the keyword here is adiabatic, means there is no heat transferred. C. The work energy, so again we will use our non-flow equation. So W will be 169.7 kilojoule. Okay, it's positive means it's work out. Okay, so this question is relatively simpler. D. Sketch the above in the PV diagram. Okay, so the initial stage is superheated, okay, at 100 bar, so around here. Okay, the final stage is 38 bar and is just dry saturated. So it must be on this line because this is the saturated vapor line. Okay, so from 1 you go to 2. That's it. It's just a general curve. Okay, can. So this is your adiabatic process. So that's it for question 6. Okay, lastly, for question 7, okay, we have a closed system, 3.5 kg of superheated steam at the initial pressure of 15 bar and a temperature of 250. Expanded polytropically to a pressure of 2 bar according to the law, PV 1.25 is equals to constant. Okay, again determine the change in internal energy, work done, heat and sketch. Alright, so to get the change in internal energy, we need both U2 and U1. Okay, so U1 can be easily obtained because we know that U1 is superheated. So go to the superheated table at 15 bar and 250 degrees Celsius. Okay, we can get the value for U1. So U1 in this case will be 2697 kilojoule per kg. Okay. Next, how about U2? How can we get U2? So as of now, we only know one of the values for U2, which is 2 bar. Okay, as mentioned previously, we need at least 2 properties in order to fully define a state. So we need one more property, and how can we get it? Okay, of course it's through this polytropic relationship. Okay, so if we want to apply this polytropic relationship, we need P1 V1, P2 V2. So we have P1, we do not have V1, but can we find V1? Yes, we can find V1. Okay, so V1 will be the V value from the superheated table at 15 bar and 250 degrees Celsius. Okay, so from the table, it will be 0.1520 meter cube per kg. Okay, so this is your V1. P2 we have, so we just need to find V2. So applying the equation, P1 V1 to the power 1.25 is equals to P2 V2 to the power 1.25. Okay, P1 is 15 bar times V1, which is 0.1520 to the power 1.25. P2 is 2 bar times V2, which is your unknown. Okay, take note over here, I do not have to change the P into SI unit because both sides are the same, 15 bar, 2 bar. Alright, so using your calculator, okay, you can get your V2 to be 0.762 meter cube per kg. So we know that now V2 is this. So the next step to do is to determine the state of 2. What is 2? Is it compressed water, saturated water, wet steam? We do not know yet. So from the saturated water and steam table at 2 bar, we look at the Vg value. So the Vg value is 0.8856, okay, meter cube per kg, and clearly this is more than your V2. So this must be wet steam, therefore wet. Right? Okay, so since this is wet steam, before we can even calculate the U2, we must first find out the dryness fraction. Okay, because this is the value that is paramount for the calculation of all the values in wet steam. Okay, so this will be V2 over Vg, okay, which is 0.762 divided by 0.8856, and this will give you 0.86. Bear in mind, dryness fraction must always be less than 1. In any case, during exam, if you find yourself calculating a value of x more than 1, okay, you better check the inputs. Okay, so with x2 calculated, we can find out our U2 by using the wet steam formula. So UF will be UF at 2 bar, which is 505. Okay, UG will be UG at 2 bar. So this is how we calculate our U2. So with both U1 and U2 calculated, we can find our delta U, which is M U2 minus U1. Okay, and if you plug in the values together with the M of 3.5 kg, you should be able to get your 1486.45 kilojoule. B. Calculate the work done. So the work done for polytropic process, it has its own unique formula, which is obtained through integration. So the formula is available in the formula sheet and is written this way. Okay, M P1 V1 minus P2 V2 over N minus 1. So we need to plug in all the values. M is 3.5. P1, okay, we need to put it in terms of SI unit, 10 to the power 5. V1 is 0.1520. P2, 2 bar, again SI unit. V2, okay, over N minus 1. So by punching in the calculator, okay, you will get this value 1058,400 joule. Okay, because everything here is in SI unit, so your output or your final answer is in terms of joule. So please convert it back to kilojoule. Okay, so this is the answer. So for C, again we apply the non-flow equation. So we have our delta U already, which is 1486.45. Q is our unknown. Minus away the W. Okay, so from here Q can be calculated to be minus 428.05 kilojoule. Okay, so this is your Q value. So lastly, to sketch the PV diagram. Okay, can initially it will be 15 bar and superheated. The final state is at 2 bar wet. Okay, so again from 1 to 2, okay, it's just a curve. So by right, you are supposed to also label your V1. Your V1 in this case is 0.1520. Your V2 is what is your V2? 0.762. Okay, can. Okay, if you look at this, the numbers are not in proportion. Okay, meaning to say I've drawn this the wrong way. Alright, so let me just do a correction. Okay, can, because 0.762 is more than 0.152. Okay, so by putting in the v value, you will see that my orientation from the previous class is wrong. Okay, it should be this way. Okay, from 1 to 2. Okay, so if there's no question, or actually there isn't any question because it's a video tutorial. Okay, pretty simple. For question 5, 6 and 7, if you have followed me during the lecture, you should do fine. Okay, so all the best for your common test. Please look at the announcement in mail. Thank you so much and have a good day.